Alright, now for the third part of the first video, it will be an atmospheric correction. Just now we talked about the sensor. We're talking about the sensor defects. We're talking about the radian. Okay, we have to standardize it. We have to normalize the value for every image that we captured. And now we are talking about the atmospheric layer. What happened during the process, okay, and how atmospheric layers will affect the quality of data and how to reduce it, or how to improve the data. So in atmospheric effect, there are two primary sources of environmental radiometric errors, which are atmospheric effect caused by radiation scattering. We learn about the atmospheric scatter, and as well as options in the atmosphere due to the molecule. So we have to remember about the relative scattering, remember about the mean scattering, remember about the non-selective scattering, which will eventually affect the quality of data. And of course, the presence of the different kind of gases, different concentration of those gases will as well in effect, okay, the absorption rate of certain wavelength given in the platforms on that particular scene, on that particular day, on that particular time. All right. And topographic attenuation as well, due to the surface, due to the elevation, due to the geographical factors which caused by the variation of geometry between the terrain and incident radiation will also give some effect. So there are several approaches to deal with this atmospheric effect, and usually all this approach will depends upon the nature of the research problem. Okay, given that if you are doing a very simple, a very basic land use, you don't really care about this, or if you don't do any comparative study between different images, you don't have to care about this. The type of data used, as we know that Landsat X is new one, so usually new satellite, okay, will have less effect or less error compared to the older satellites. And available information concerns about the atmospheric condition at the time of the image acquisition. Okay, we are quite lucky because we are in equatorials, okay, and we have the highest solar exposure, the highest solar radiation. Okay, however, there we also have the problem about the humidity, but because of our areas, okay, we have a quite consistent temperature, we have quite consistent situation, so we don't really have this much problem as compared to the southern and northern hemisphere, where they have this four seasons. We have this different kind of humidity range and so on for every season, for every equinox and so on. So therefore it might be a more concern on that data on that area. And of course, how accurate the biophysical information can be extracted from data. Okay, so here if we talk about the land use, you just trying to classify between different kind of land usage based on the socioeconomic activities. So a very good a very is quite what we call it is quite, the classification is quite coarse. Okay, and also we don't really care about little tiny things such as if it's vegetation. So what kind of vegetation will be? Is it a plantation? Is it a, of course, plantation you can simply detect. Or if it's plantation, what kind of plantation it will be? Is it oil palm? Is it coconut? Something, or is it paddy and so on? So we don't really care about this if you're doing the land use, where because of the data can we can just simply classify them in the what you call it, in the lower category. And if we go for the high category, usually what we did is we also depend on the data from the ground, as well as some auxiliary data such as aerial photos, previous map, and so on. Right. So most land cover investigation ignores the atmospheric correction problem, so we are safe. And it is assumed that variation in the signals of varying land cover is great enough to overcome the effect of the atmospheric noise. It has been shown, however, that atmospheric often improve classification result. Yes, you don't really care about the atmospheric correction, but if you want try to improve some of the data, especially when we are using legacy satellite platforms such as Landsat 5 is quite old, so we can try to do the atmospheric correction. It's good. And however, if you are doing the biophysical investigations, you want to detect such as chlorophyll content, you want to detect a plant head, you want to detect some species, so you must do this, right? And when such corrections are required, there are four approaches which are possible. The first one, calibrate remote sensor data to consider in situ biophysical measurement. So we are bringing the apparatus, we are bringing the weather station, we are bringing the solar radiation meter, and so on, where the limitations are costly, time consuming, and cannot usually extend result across space and time, or the other way, use the existing model atmospheric effect. And however, it's useful if attenuation is small compared to the trend signal. So usually what happens in Malaysia, we are quite lucky because we can just simply use the model due to our environment. And model atmospheric effect in conjunction with coincident in situ. So by using the model, and of course we try to improve, or we try to get some extra data or precise readings using the in situ measurement. Okay, and this is what we call as a it allows the fine tuning of atmospheric model for local conditions, because for the atmospheric model it is quite general for the whole world, and this also called an absolute radiometric corrections. And the other things also we can use is multiple looks, which we look into more than one sensor position or more than one band. And this sensor position will suffer because of different atmospheric path, and multiple band method is better because a signal path is sensed, which are called relative radiometric correction. Okay, so when we talk about this atmospheric correction, we know that solar radiation of the EMR is largely unaffected on its journey to space because it's vacuum. Nothing can uh, influence the energy being transformed, the photon being transformed. But upon reaching the Earth's atmosphere, however, it is selectively scattered and absorbed. Of course, we learned before that some of the gaseous elements, such as CO2, such as carbon dioxide, such as ozone and so on, they absorb quite a number of wavelength bands. Okay. However, it is selective, scattered, and absorbed, and the sum of these two forms of energy loss is what we call as a atmospheric attenuation. So these are all the atmospheric attenuation. Okay. If you look here for the nitro oxide, they are quite susceptible for the absorptions within this wavelength. Okay, 3.5 to 4 micrometer, which is short wave infrared, and the other one will be between 7 to 8 micrometer, right, for infrared. However, for the O2 and ozone, for the oxygen and ozone, if you look here in the UV range, most of the radiation will be absorbed by the ozone elements, and some of it will be on the far infrared, will be absorbed by the oxygen. For the CO2, they have three range of the wavelength will effectively absorb it, which is a range of 2 to 3, 4 to 5, and more than 12, which is middle infrared as well as thermal. For the water, most of the wavelength will be absorbed by water elements, so water vapor. So water vapor could be cloud. That's why we try as much as possible to trying to not to use data that have a great cloud or dense cloud covers, okay, due to this. Okay, so now here, this is what we call atmospheric attenuation window or atmospheric absorption window. From here, you can see what wavelength and what type of gases that effectively absorb the wavelength. And when we say about absorptions, there are no reflection at all. They will be totally absorbed. Okay, They are not reflected on the surface because it's being absorbed through the journey from the sun goes to the surface. It never reach the surface, and what happened is no reflection on that particular wavelength due to absorption.